So here what we do, we have about 1 hour. I will go to the last section of this paper. It's called Ergodic Ramsey Theory and Update. It was written in 1996. It is on my page. And my page starts maybe with words, some recent preprints. It tells you for how long time I didn't update it, but this one is there. So, and it starts it. So, okay, so you can easily download it. And there is section 5, which is devoted to open questions of different values of importance and difficulty. So I don't know, since time is running, for some of the questions which got advancements, sometimes very recently, I will just give you brief references and we'll move on, because I want to have time for everything. So, very first question. Some of these questions are more of interest, or at least a priori more of interest to ergodic theory than to combinatorics. They all can be maybe translated to combinatorial questions. So, for example, assume that x, b, mu, t is mixing. So this means, of course, mu of a, t and a goes to mu of a square. Usually they define it for a and b. So mu of a intersection t and b goes to mu of a times mb. It turns out that that's all you need. Okay, that's separate easy exercise on Hilbert spaces. So let's take this as definition of strong mixing. Any set tends to be independent with itself. And so question was, is it always true? Is it true? So this is for all A. That for all n non-zero, mu of A, t and A is strictly bigger than mu square of A. And for all n, or mu of, let's put it smaller here, and for all n, mu of A, t and A strictly bigger than mu square of A. This is something which you may want to call over-recurrence or under-recurrence. And when I formulated it, I thought it just fun, easy question. I actually thought that maybe you can create it with sets in Z and then move in reverse way to measure theory. It turned out to be harder, and some people tried, and recently it is nice preprint about that. So I will just give you reference and let me move on. It's a very nice advancement in this question, and the answers are sometimes surprising. So that maybe will stimulate you too.
So the question is that either one of these?
No, I want both, actually. My question was whether, well, I asked, how about this, how about this? So in principle, you would like both to be true. And you may want even to expect that if one of them true is second true, but in which order?
Can you maybe formulate it again?
Suppose you take this as two different questions.
Okay.
Is it true that, I see, wait a second, that there exists A such that? I see now why you asked your question. Yes. Now you are tired from the first day, I noticed it, but I'm also tired by now, so please watch what I'm doing. Now, I don't want to spend too much time on this. I just want you to encourage you to go and look at very nice recent paper. It's an archive. And this is paper by Boshernitsyn, Frantsikinakis, and Waerden. The names are so special you will find it easily. They answer this question in more than one way, and it's very nice. All right, I'm moving to second question. Second question was, so here I want to spend a little bit time. So a set S in N is called a set of recurrence if for any x b mu t, for any a positive, there exists n in S such that measure of A intersection T minus NA is positive. I hope it's totally clear why it should be called set of recurrence. This is a set along which Poincare recurrence takes place. And so examples are obvious and trivial. IP sets, n cube, primes minus 1. There are many, I say trivial, I was wrong. Many non-trivial examples as well. So shifted primes is an example of this. Cubes or any polynomial with zero constant coefficient surely is, okay? So there are interesting sets. And so not hard to show that if S is union of Ci, then one of Ci is also a set of recurrence. Exercise. But set of recurrence on its own is a good notion, but maybe for a physicist it's not good enough notion. Because if you know that this is positive, maybe it's so small it's invisible. You want recurrence, the rule with some constant from below. In optimal way, and these are the sets which I mentioned, so let's call a set S is a set of nice recurrence. If for any x, b, mu, t, for any a with measure positive, for any epsilon, there exists n in S such that measure of a, t minus n a, bigger than mu square of a minus epsilon. It cannot be better than that. So this is nice recurrence. And all the sets I mentioned above are examples actually of nice recurrence. And you have to work, but there are examples of sets which are not nice recurrence. So there is a nice paper by Alan Forrest about that, and later by Randall McCutcheon. So let me just, not all sets of recurrence are sets of nice recurrence. So Alan Forrest, Randall McCutcheon. Randall McCutcheon has a paper which describes Forrest results, so maybe that's easier reference. Three results in recurrence. I think that's the title. You can find it. And in paper of McCutcheon will be reference to Forrest. Okay, so that's background. Of course, if you do ergodic Ramsey theory, partition regularity is important. It's also useful, because if you know that in one system you got this, and in another system you got similar thing, you want intersection to be maybe non-trivial, and you want it to be for applications at least bounded from below. So open question remains, which is this. Open question do sets of nice recurrence possess Ramsey property, or that's too fancy language. Are they just meaning, are they partition regular? Open. Very annoying. You have totally natural condition. Works for any set in any system. You finitely partition it. Prove or disprove that one piece is still set of nice recurrence. Any result of this kind leads to new questions, but before I will ask new question, answer this one for me. Okay? So let me move on. Here is a sort of a specialization of this question, which is also very annoying. This will be better understood by people who deal with ergodic theory. It may have connection to times 2 times 3 famous problems. So let me formulate it. So is the set 2 to the n, 3 to the k good for recurrence of weakly mixing systems? So all I want that for any A in weakly mixing system, it will be. So why this question is non-trivial? You remember weak mixing systems, I mentioned it at least, they behave well only along sets of density 1. This set is of 0 density. Okay, so this is too small set generated by only 2 primes. It's a set of 0 density. Any set generated by finitely many primes is of 0 density. That's why it well may be that it falls into that set of exceptional 0 density where you don't have anything. But our experience shows that if you have a nice set, you remember my example with mu of A, this is definition of weak mixing. This goes to mu square of A if n is not in some set of 0 density. This is still weak mixing. So as long as you take nice sets along which you go to infinity, we are used at least to polynomially growing sets, that things are nice. And this is sublacunary but super polynomial. So it's a very annoying intermediate case. If it would be, no one asked this question. I remember asking you about Sarkozy theorem for other right-hand sides. So if it would be 2 to the n, maybe it would be easier. But it is 2 to the n, 3 to the k. And it immediately makes the set larger. And the question is interesting. And if the approach to solution will be through harmonic analysis, then chances high it may be connected to times 2 times 3 open problem. What?
And you leave only 2 to the n?
No, for 2 to the n, I think you can kill it. Okay. No, but in general, lacunary sets, they are good for rigidity, but they're also good for killing recurrence, as a rule. So I hope I'm not cheating now. No, about rigidity, I'm sure, but about killing recurrence, I know they kill recurrence. Yes, I think I'm right. So lacunary sets kill recurrence in general, and because of recent papers by Kanigovsky and Touvenot and Kanigovsky and Fayad. So you can realize this killing of recurrence on level of weakly mixing systems. So those questions become delicate, and I started formulating them only for single recurrence, and it's already delicate and maybe connecting, at least in this way, only to harmonic analysis in a way. But answer this question, I will ask next one. So all these questions are of the sort that it's natural to ask next one. All right, so I already discussed it. Let me very briefly discuss, because that's, as we see, is not exactly applicable, easily applicable part of ergodic theory. So 1 over n f of t n square x converges almost everywhere to some limit, okay, for any f in Lp bigger than 1, but not necessarily in L1, and people to mention would be Buxolich and Molden, 2010. And Patrick La Victoire, 2011. This is very French name, but he is American, I think. So La Victoire, if you go, and he published very few papers. I think he left mathematics, but if you want to read about this, go to papers of Patrick La Victoire. It's easier read. Now, there are many other things you can do about almost everywhere convergence, and it would take us far away, but there is one thing which is, again, known. This is, by the way, Bourgain, and known, Bourgain again, that 1 over n f of t a n f f1 f2 of t b and x converges almost everywhere for any, say, f1, f2. Let's take for convenience in L infinity. Here you can put it up to LP spaces. That's not the problem. The problem is how to make 3. So open is this. Open and maybe wide open. 1 over n, f1 of t a n, f2 of t b n, f3 of t c n converges almost everywhere. That's wide open. And when I say, of course, there are special systems for which it's known, but it's on level of distal systems, something pretty non-general. Interesting, but not general.
Is there any restriction on the ABC?
Any integers. You want here any, for any a and b in n, and here for any a, b, c in n. And this is annoying because it's natural to ask, and Bourgain's proof is very sophisticated. And that's one of the reasons that this should be even more sophisticated result. So people who like pointwise convergence, that's a challenge. All right. Now, so let me discuss another problem which had a solution already. So I don't know what can I, maybe I should start erasing a little bit. So we discussed already. I just kept it. So in previous version, I was not careful about quantifiers. This is the correct order of quantifiers. please take a note so that no one will be confused. You have a set, and you want to find its model. And this model should be such that for whatever shifts you would do, it will be imitated by dynamics of T. And now I will erase it, okay? Okay, and so here's another interesting thing. So this is definition. A topological system xt is uniquely ergodic. Well, you could guess that it's uniquely ergodic if there exists unique invariant measure. But equivalently, and that's, again, goes back to works of Oxtoby and Furstenberg. So uniquely ergodic if for any f in C of x, lim 1 over n f of t and x equals integral of f equals constant, which turns out to be integral of f d mu, for every x. This is a rare case of convergence, which is not even almost everywhere convergence, it's everywhere convergence. And this luck is available only for continuous functions and for uniquely ergodic systems. And that, of course, is behind many applications of ergodic theory to theory of uniform distribution in number theory. So that's an important class of systems. Well, but all I was, trying to popularize was the statement that take any theorem, replace n by n square, or any polynomial, it will be still true. When it comes to recurrence, when it comes to Szemeredi theorem, we know this all true. So for recurrence, Sarkozy is there. For multiple recurrence, Leibman and myself extended Furstenberg. For IP star recurrence, Makachin and myself extended Furstenberg-Katznelson. So polynomial business is great. So I ask this question, naively ask the following question. Is it true? So now assume in addition that t to the n, t to the k is uniquely ergodic for all k and minimal for all k again. So I assume even more. I assume that t is as good as it goes. You see, in general, unique ergodicity and minimality are literally different things. But I assume everything possible, anything good. Uniquely ergodic at every power is uniquely ergodic. And minimal and every power is minimal. And what I want that along squares, or say polynomials, that will be behaving well, okay? So is it true that for all but first category x in x, 1 over n f of t p of n, take square, that's interesting enough, goes to integral of f. Since I assumed even more, and if I am compromising here, I say not for all, just for almost all in topological sense. And I hope that the answer will be yes. This would be good. This would be still not as good as unique ergodicity gives you for all n's, but up to negligible sets from point of view of category, it would be great. Guess what? The answer is no. So answer, no. And this is, so I will refer you to paper of Roni Pavlov, ETDS, 2008. And then see also Yuri Lima, ETDS 2012. So Lima extended it to polynomials of many variables and did something else, but the breakthrough was first done by Ronnie in 2008 as part of his thesis. He did other good things in thesis, but this was part of it. And so he showed examples where actually it fails to converge on set of category 2, on meager set, on co-meager set. So what it teaches us? That you should be optimistic, but with some measure. Well, you should be not always optimistic with unique invariant measures. And so it's interesting. But
in the circle, this is no.
what? Right.
In the circle, this is no.
For isometries, that's easy. Because for isometries, things are fine. That's because of n square alpha being uniformly distributed. So if you take any rational rotation, you're in good shape. You still can maybe be lucky with skew products of algebraical origin. But then it doesn't work. Okay? All right. Now let us move on. And so don't know. I have only half an hour. The next question, the best framework for it would be polynomial version of Hales-Jewett theorem. And I even didn't formulate it before. Let me skip the next question. At the very end, if I have time, I will touch on Hales-Jewett theorem. This is a big deal on its own. If I will not touch on it, I just tell you right now that question 6 is still open. And so... But question 7, so just to make it faster, I will start giving you a number of questions and references. That's already some information. So question 7, so question 7. Are there sets of K recurrence which are not sets of K plus 1 recurrence? I hope it's clear what it means. So you have, like in Szemeredi theorem, intersection of K terms, but along the set of recurrence, but not K plus 1. Polynomials, or IP sets that I mentioned before, or primes, we know this too, they are sets of recurrence for any length. They are good for Szemeredi type theorem. But maybe there are sets which are good up to here and then not longer. And yes, and this is a nice paper by Frantsikinakis, Lessine, and Waerden. And it was published in Annals of Annals de l'Institut Fourier. (2006). Okay. Now, a very nice paper. Result turned out to be a little bit easier than expected. Very neat. And somebody asked about translations on Nil manifolds. It's about skew products, which are already close to translations on Nil manifolds. So the counterexample comes from algebraic skew products. Okay. Now, next question. I will skip, it's still open, and question 9 was recently answered, so here is a general question of importance. At that time it was wide open, and since then it's solved. So question 9. So does the limit, does the following limit exist? So 1 over n, f of t1 p1 of n, f of t2 p2 of n, f of t k pk of n. So pi's are polynomials, ti commute, and convergence is in norm, because as you already saw by previous discussion, I asked about norm and pointwise, but pointwise is far away until now. So this is fundamental question, and why it is so fundamental? Because expressions of this kind, that's what exactly Sasha Lehmann and I use in proof of Polynomial Szemeredi theorem. So they're totally fundamental expressions. And we know that they converge under some weakly mixing assumptions and other things, but in general it was wide open at that time. And recently there is beautiful work by Walsh, Miguel Walsh. Yes, he published it a few years ago in Annals, 2012. See also Austin for a different proof in 2015. And also Zorin Kranich to appear, but you can find it on his website. So what Walsh did, he showed that not only this is true actually. So Walsh showed that this is true when Ti generate nilpotent group. Now, this could be expected that for nilpotent it would be still true, because polynomiality is totally inherent for and connected with nilpotency. It's already for general commuting ones. And by the way, for single T, it was proved before by Horst Krah and more generally by Sasha Lehmann. But for commuting Ti's, you needed something totally new, because it was no structure theory known. And the interesting feature of the proof of Walsh is that he doesn't use any structure theory. It's he proves that this is Cauchy sequence, hence convergent. It's beautiful, and I think Austin's proof is easier to read to ergodic people, but it's a very nice induction, okay? And Zorin Kranich generalized it to actions of amenable groups with some polynomiality, and Zorin Kranich result is very useful for quotations when you need to do things in more general setup. So these are all great papers. Okay, let me keep moving. Okay, so next question is also solved, and I will tell you about it. It's question 10. So question 10 was the following. I think I can erase here. So assume that X B mu T is totally ergodic. So Tk is ergodic for all k. And assume that PIs of n are independent. So I assumed in this question, this is question 10, I think, 10. So question 10. So I assume that they have different degrees to make it easier, but the right question is about independence and what answered in this way, okay? So is it true that 1 over n f of t p of n f2 tp2 of n f of t pk of x converges to product of integrals of fi's. So let's try to understand what it is about. This is about independence in norm, of course. Everything is in norm. So this is about independence along independent polynomials. So if k equal 1 and t is totally ergodic, that follows from what I explained earlier today about the proof of Sarkozy theorem. So when t is totally ergodic, you have correct limit. And now if you have two polynomials, say like n squared and n cubed, maybe n squared and n cubed are independent because of these polynomial actions are independent, and maybe then the tendency will be to independence. So this was my question. And the answer is yes. And it was given quite in very nice paper by Yes. So this is paper by Frantsikinakis and Kra. I think it is ETDS, is it? No, Israel Journal. Israel Journal. 2005. So what is nice about this result, so for weak mixing, we knew it before. And then for any polynomials which are distinct, this is my older result, which is called weakly mixing PET. And that's what is needed for polynomial Szemeredi theorem. But you want to take to extreme the phenomenon of independence. So you don't need maybe weak mixing if you assume in addition, instead of just polynomials being different, you assume that they're independent. And that's exactly the answer. So the answer is yes. This is a special case of today of more general results. They all have the same nature. If you have different rates of growth, if you have reasons to believe that actions are in general position, then jointly they are independent. But this is the beginning of it. Okay, good. Let me move on. I already told you, and I don't want to spend time on this, we still don't know any reasonable general this is tantalizing open question if this polynomial is partition regular, and there are some advances in this direction, especially in papers by Host and Frantsikinakis, and they work very hard, get beautiful results, but they don't get to this. They get some other quadratic forms with z not from the same color, and even to get that, they really develop very important theory related on multiplicative number theory. So what they do is great, but still not enough. So I'm not sure what is the right approach, but that's still open. Okay. Now, I will skip question 12. It's number theoretical, coming about irrationalities of sorts, open. And then I will go, so now I want to touch, I still have only 15 minutes. Let me touch a little bit amenability. So there is one conjecture, and which was solved recently. It has no number, but it was a conjecture before question 13, and it was answered recently. So I think I can erase a little bit. So assume that G is, say, countable amenable group. Somehow I understand that majority here knows what is amenable group. So you may think about abelian groups which are different from Z, but the most important part of this question is about non-commutative abelian groups. So, and assume that TG1, TGK are commuting actions of G. So very general ergodic theory, right? General group acting, and you have finitely many commuting actions. And the very first thing you want to know if such limit exists, and it does, because this is just for Neumann ergodic theorem, and it is practically with the same proof. The only look at this theorem. Instead of taking t to power n, I take t sub g. But I average, instead of 1 over n, I average through some sequence of sets which are called Fellner sets. And if you take Fellner sets for averaging, then you expect the result to be projection on invariant function. So that's easy, at least a norm. Not a norm, it's very hard, but was proved for specially creatable Fellner sequences by Elon, Lind, and Strauss, beautiful result. But what I'm asking now is about multiple recurrence, so this is first primitive case of it. And so I want to know how about this. So this is Fellner sequence. A Fellner sequence. And so I'm interested now in multiple recurrence. By the way, from here it follows that G, for which mu of A intersection TG of A is bigger than mu square of A minus epsilon, is synthetic in G, and all for the same reasons like hinge and recurrence theorem. So that's formally much more general, but it's the same business. But what I'm asking now, it's already much less obvious. And let me first of all even formulate it properly. So I'm interested in multiple expressions. Pay attention. So instead of spreading, so naively, if you start dealing with this, you maybe would guess that you should deal with something like this. This turns out to be a wrong expression. You have to add one at a time. So on abelian level, you would not see any difference. It's about such triangles or such triangles. And in abelian world, they are symmetric in every possible respect. But in amenable world, if you take a G plane, G cross G, and if you take sets in G cross G, such sets or such sets are not necessarily the same, or such sets. So, and the right ones, as it turns out, are of this kind. So the correct expression would be this. It is this result exactly which we proved together with Randall, so McCutcheon, Zhang, and myself. And for a while, it was the best thing we could do. So 2 commuting actions, you have Roth theorem in very general form. Roth theorem is like Szemeredi just for triples. And then it was for a big while open what happens for more general triangular expressions. And then it came Austin. So just recently, Austin, yes. So for convergence and recurrence. This, by the way, result was not lim super in lim, it was lim, but I repeat, only for 2 actions, and he did it for any k. And that's very nice. I'm not sure it appeared already, but it's Tim Austin norm convergence of amenable ergodic averages. Okay, now, you know what? I will now attempt to explain what is Hales-Jewett theorem. This way, anything which is mentioned in my program was covered, and some things which were not mentioned also were covered. So, and this is the final and still widely open question whether polynomial Hales-Jewett theorem is true. But it's impossible to talk about this until I will tell you what is Hales-Jewett theorem. So let me start there, and I hope I will not confuse you too much. So, by the way, in those cases where answers were given, there is still what to do. For example, Austin result, which is great and strong about Cesaro averages, it still doesn't give us all the complete information about those generalized multi-correlation function, which is the expression that you average. Its additional properties are very interesting, and because group a priori is not amenable, or not abelian, then there is no harmonic analytic really feeling about this. In any case, so here is something about Hales-Jewett theorem. So this is about generalized tic-tac-toe game. That's at least how they intended it. So they thought it's application of combinatorics to theory of games. So they generalized van der Waerden theorem. And they have curious paper in Transactions of IMS about 50 years ago. We had a conference recently dedicated to 50 years of Hales-Jewett theorem. But so what Hales-Jewett theorem tells you? So it looks different from what we used to, but I can make the case that it's natural generalization of some theorems that you know. So let A be a finite alphabet, and T an additional symbol, T not in A. So combinatorial line, so is you know, before this, so let W n of T denote the set of all words over A union T. So far it's not so bad, right? I take all possible strings of symbols coming either from my alphabet or sometimes T will be there. Of length n. And so let W be an element of W n of T, and assume that T is present in W. I hope it's also not hard to understand. Some word where t appears. And now we can define combinatorial line. This is W of t when t belongs to A. And as you see, it has k elements. And I will give an example now for you to feel better. So suppose my alphabet is, I don't know, 1, 2, 3, 4. This is A. And suppose my word is 1, 2, T, 4, 1, T, 3, 4, T, TT. So what would be combinatorial line induced by this word? Well, it will be this. 1, 2, 1, 4, 1, 1, 3, 4, 1, 1. Then 1, 2, 2, 4, 1, 2, 3, 4, 2, 2. 1, 2, 3, 4, 1, 3, 3, 4, 3, 3. And finally 1, 2, 4, 4, 1, 4, 4, 4, 4, 4. This is combinatorial line. I hope it's clear what we did. So some letters stay what they were, and some move simultaneously as t is substituted. Sorry? T is not in A. That's why this is a meaningful thing. Oops. Wow, thank you. I said not in A, but I wrote in A. Yes. Okay, T is not in A. It would be no sense in this otherwise. That's why I wrote here union. All right, I become happier now? So T is not in A. And we have notion of combinatorial line. And so here's theorem, Hales-Jewett. If R is fixed and N is large enough, then for any coloring, so Wn of T being union of CIs, one of CI contains combinatorial line. Well, for people who do combinatorics, it's a very natural theorem. Now I want to connect it to what we know in Ergodic Ramsey theory. And now I will just say a few sentences because time is running, but they all should give you stimulus to read the end of my survey, because there I explain way better about Hales-Jewett theorem, about its polynomial generalization that Sasha Leiman and I have. This is polynomial, Hales-Jewett for partitions. Even to formulate it, you have to work a little bit, but that has until now brought perhaps the best application. So that's really fundamentally useful thing. And the open question is density version of polynomial Hales-Jewett. And that's what is explained there. But at least now I want, in 1 minute, explain that this is surely better than van der Waerden. Let's understand that. Where is van der Waerden here? Very simple. Think about numbers represented, because of my picture, numbers which are represented in base 4. So you take all numbers of sufficient length represented in base 4, and you finally color them. And in one piece you will have, so now it is not symbolics, it's numbers. You'll have this number in base 4, and this, and this, and this. And I hope it's clear that the differences between these numbers are the same. This is progression of length 4. If I would take any other base, it would be progression of length n, k, whatever it is. Okay, so this theorem contains as a very special case van der Waerden theorem. And moreover, finitistic van der Waerden theorem. Now I could, instead of this, consider this group. This is the vector space over finite field. Its elements are naturally, because ZP is finite field, its elements are naturally identifiable with strings of symbols from your finite field. You finitely color this. So this is vector space over ZP. ZP is field of P elements. If I apply in this coding Hales-Jewett theorem to this space, the end result, which you will take my word, because you have to think, if you see it first time, maybe it's not immediate. The end result is that there exists a fine subspace of arbitrarily high dimension. That's actually finite characteristic analog of van der Waerden theorem. So you see, Hales-Jewett is rightly called mother of combinatorial theorems because it gives so many of them so immediately. So what Furstenberg and Katznelson did, they generalized this Hales-Jewett theorem to density version. Similarly, like van der Waerden goes to Szemeredi. So because of Furstenberg and Katznelson, you have density Hales-Jewett, that's Furstenberg and Katznelson. And now there is polynomial Hales-Jewett. That's Sasha and me. So and now it's totally open, and that's what I discussed at the end of that survey. If density version of polynomial Hales-Jewett theorem is true. So the proportion, the analogy is clear, right? So this is like Szemeredi, and this is generalization of P of HG, which would be van der Waerden. Then Sasha and I have polynomial Hales-Jewett. This is like polynomial van der Waerden. And we do know that we have polynomial Szemeredi, but we don't have density polynomial Hales-Jewett. This remains perhaps the most tantalizing and maybe important even in combinatorics open question. Ergodically, there are many other nice things around this, but for combinatorics, anyone who will do it will have easier way of getting tenure. So at this positive note, and I wish that one of you will do it, and please read this survey, and I have other surveys, so material that I managed to cover is small percent of what is there known in this beautiful body of Ergodic Ramsey theory, which connects to many other sciences. I didn't have time to talk about primes. There are increasingly interesting connections to primes and to multiplicative number theory, even to questions related to so-called Sarnak's conjecture. Work is going on. It's a very rich area, and you are young. I invite you to be interested in it. Thank you.